Okay, today we're going to talk about moisture or water in the air. Water is a big component and major influence on our weather. And of course, it's part of the weather. We all wonder, oh, is it going to rain today or is it going to be cloudy? How much sunshine am I going to get? It influences a lot of sometimes our daily decisions. For example, I'm going to a birthday party for some of my family today, and where we're going has a pool. I want to know if it's going to rain, whether I can go swimming or not. And since there's supposed to be a chance of thunderstorms this afternoon, I may have an issue with it. So understanding water and how role it plays in the atmosphere is big. There are various aspects to water. There's evaporation. Basically, evaporation is where water molecules are leaving the ocean, for example, or a pool or a puddle, and moving into the air, into the atmosphere, faster than they are on condensations occurring, where they would go back into the water. So more of the water molecules are leaving with evaporation. Then they reach a certain temperature and they cool off and they begin to condensate. And condensation is just water droplets forming, like dew you see on plants sometimes in the morning. And they may occur in clouds. And then this water comes back down out of these clouds in precipitation. Maybe it's rain, maybe it's snow. Oh yeah, and you can get even from ice sublimation, where the ice is, or snow, is being pulled back into the atmosphere faster than it would be reaccumulating or replenished. And I've seen this in the wintertime, and I'm sure you have, where I see all this snow on the ground and all this snow on the roads, and I wonder, well, why is it going away? Well, it's sublimation, a lot of it. And that's what's causing that snow to go back in, that water to go back into the atmosphere. Oh yeah, plants play a role. It's real curious that they play a role, because you can look out into places like Oklahoma, for example, where they plant a lot of winter wheat. And if you look at the moisture in the air during the early summer in Oklahoma, it's a lot higher than when they harvest that wheat. So that wheat, our planting of wheat, actually has a role to play in the amount of moisture, for example, that's in the air in Oklahoma and in other areas where large crops are planted. You can really see the difference. So this is just a whole water cycle. Oh yeah, the water is going to come down into the ground, and places like roads and stuff where it's not going to run off. It's going to run off somewhere into streams, and sometimes it comes down, lands on flat land, and just slowly works its way down into the ground and becomes water, part of the water table that's well down under the soil usually. My water table around here is a lot closer to the surface than yours is in Ohio. However, if it rains a lot in Ohio, your water table is going to rise. Mine doesn't take as much rain to get up here. So that's just all the aspects of what happens with water in the air. So with that, we talked about all the different aspects of it and the balance sheets and everything with it. Measuring water is the other thing I wanted to talk about a little bit here. There are things called water vapor in the air. We call it water vapor. We call that has a pressure. Remember, we just talked about atmospheric pressures and how each gas adds up to a certain total pressure in the atmosphere. Well, water vapor contributes to that. It has an air pressure. So as the more water vapor arrives, the more the contribution to air pressure becomes from water vapor. So you can literally say water vapor has a vapor pressure. And that is a measure of water vapor. If you know the amount of vapor pressure in the air, you know something about water vapor. Mixing ratio is just basically the mass of water vapor in the dry air. It's just a mixing ratio. It's expressed as grams of water vapor per kilogram. These are all terms that are used in meteorology to describe moisture. or water in the air. Specific humidity, the mass of water vapor per mass of any kind of air, even containing the water vapor itself. So that's the difference here is mixing ratio only looks at dry air. Specific humidity looks at air that even contains moisture. They're very close and they're pretty much almost equivalent, but they're not quite. Absolute humidity is the mass of water vapor per volume of humid air, normally expressed. Again, all of these are masses, the amount of grams of water in the air. So, saturated air, it's when the water vapor reaches a point that the air can't hold any more of it. In the summertime, hot humid air can hold a lot more, hot air can hold a lot more water than cold air. In the wintertime, if you ever look at something called dew points, and we're going to talk about that here in a minute, it's a measure of moisture in the air. They're much lower in the wintertime than they are in the summertime. One aspect of water vapor, like I say, can hold be a tremendous amount of it in very hot air. Saturation vapor pressure, which is just another, we talked about that here a minute ago. If you had it 50 degrees Celsius, and that's 122 degrees Fahrenheit, hot, it can hold 123 millibars of vapor pressure. Wintertime, temperature is down to, we'll say, 23 degrees. It can only hold 4 millibars. That is a tremendous amount of difference. One of the things, though, here, notice that over ice, the amount of vapor pressure is lower. Instead of going 4.21, it's 4.02. A little bit colder, it's 2.86, 2.60. That is extremely important in understanding why precipitation occurs later. So remember that over ice, it doesn't take as much water vapor to saturate as it does over liquid. So we're all used to hearing the term relative humidity. Well, relative humidity is just whatever the vapor pressure is now divided by the saturation vapor pressure, which we just saw a table of, times 100. So it's basically the percent of water that the air has capacity to hold that's right there now. So if you have 100% relative humidity, that means the air is completely saturated. Now, that doesn't mean that the air can't start maybe putting out dew. It does at night sometimes and actually cool down more. So it can get rid of some of the moisture in it. So the temperature can actually change while this is happening. But that is just part of the process with water vapor. So let's take a look at a couple things here. A measure of water vapor is understanding precipitable water. Precipitable water is if you just dumped all the moisture out exactly in that column of air over your house. So for example, right now in Ohio, it's a little bit on the greenish side, which now this thing grows up to about 2 inches or so up in this area, so there's a lot of moisture up in New England right now from where Faye went through. However, you're seeing some drying come into your area. You can actually kind of plunge it down a little bit here. Oh yeah, the desert out in the west right now, it's pretty dry. And there's a big desert actually in Chile. I never really thought about it until I learned a lot more about meteorology. But some of the driest desert in the world is in Chile. And you can see it is extremely dry there. Look along the equator, or the intertropical convergence zone, and you see lots of moisture here. And in the Gulf of Mexico. So these are areas where if I'm watching the weather and I'm seeing a storm develop, I want to know, is my moisture coming from some of these monster sources of moisture? Or is it maybe coming out of the mountains or coming down out of the Pacific where there isn't nearly as much moisture that would make it to my house? It can play a big role in the amount of precipitation I get. Here is the last day's dew point and relative humidity for Columbus, Ohio. I could have chosen anywhere in Ohio. I just picked the middle of the state. So when we're going along here, I want you to notice temperature and dew point. They are green is relative humidity. The dew point is in here in blue is the temperature. So yesterday in the afternoon here in the morning, your temperature was 80 and the dew point was 69. Your relative humidity was 69%. During the day yesterday, moisture actually arrived in your area. Even though the relative humidity went down, the amount of moisture or dew point went up. It's 71. There it started dropping because you had a thunderstorm, it looks like, right in this area here. You had a lot of things. And here is the wind that actually shows with it. And here's the amount of precipitation that the airport had during that time. So you can pick up all these things from this little graph here and see that during the day, the dew point may actually drop as the air is getting heated, it mixes. But during the afternoon, late evening sometimes, evaporation from plants begin to provide more moisture. So the dew point can actually rise in the late afternoon, evening again from the plants. So it's not a static thing. And moisture can be advected in sometimes. But relative humidity, if you think about it, it gets hotter and hotter during the day. It can hold more moisture. So the relative humidity is going down. So one last thing we're going to talk about is stability. Okay, stability is the amount of how much air parcels want to rise. If you put an air parcel out there and the air around it is warmer than that air parcel is going to want to sink. Why is that? Well, cold air is denser than warm air. So when you look at an air parcel, think of it as being any size you want. Typically, make it whatever, 100 feet across, I don't care. But that air parcel has one temperature. The air around it, the bigger air, has another temperature. Here's an atmospheric sounding for Springfield, Missouri. Springfield, Missouri today has an enhanced risk of severe weather. So it's going to be a nasty day out in that part of Missouri today. Why is that? Well, down here this morning, you can actually see the temperature cooled and it's actually warmer at about maybe 500 feet off the ground than it is at the surface. So that happened because of that cooling we get with temperature at night, radiation pulling out from the ground, cooling it, conduction at the ground. So you have a cool layer right there. But if I heat that layer, and today it's going to heat, there's going to be sunshine right now out there. So say it gets up into a temperature, this would be approximately close to 88, 87 degrees. If it reaches that temperature, the air around it at that point is cooler than that air parcel. So that air parcel is now warmer than the temperature around it, the environmental air. So it's unstable. It's going to want to rise. And if it reaches a certain point and it reaches saturation, remember when the air parcel saturates, it gives off latent heat because of condensation. When it does that, the 80, instead of following 9.8 degrees Celsius, like the outside air temperature might be doing, it's following the path of about 6 degrees cooler. So that's about a 3-degree change. Well, in his case, it is really, really cooling with height here in this part of the atmosphere. But if we assume this air parcel is saturated, it's over here. If you took at the temperature difference here, it would almost be 10 degrees. And one of the things about stability is it causes an acceleration. So it's actually picking up speed, that air parcel. So instead of going maybe at 1 mile an hour, it might be clocking along by 60 to 70 miles per hour up in here somewhere. And when you get that kind of rising air, that's what causes severe weather. That's what causes big thunderstorms. So that's what's happening today out in Springfield. We're getting very unstable air, where the air parcel is way over here, much, much warmer than the actual environmental air. So this is one of the things here is the LCL again is right around in here somewhere. And that is where the saturation occurs. That's where the base of the clouds would be. So this is the first section we're going to talk about. I hope you got something out of this. We'll move on into clouds and precipitation in the next part of this now.